Hello everyone, my name is Yu Yaoge and I'm a PhD student at the Institute of Computing Technology, Chinese Academy of Science, working under the supervision of Professor Shenghua Liu. Today, I'm excited to present our work on can graph descriptive order affect solving graph problems with LLMs. Previous research have shown that large language models have preliminary graph reasoning abilities. However, we noticed something interesting. Well, researchers have explored the different prompting methods and graph encoding functions. One critical factor has been consistently overlooked. Could the order of graph descriptions be a critical yet overlooked factor? Let me show you why that matters. Here's a simple example. Look at this benzene ring structure. On the left, we present edges in a logical order, C1, C2, C2, C3, and so on. Humans can immediately recognize this as a benzene ring. But here, we present the same edges randomly. Humans need extra effort to understand the structure. This raises an important question. If order affects human understanding, does it also affect LLMs? This observation led us to formulate three specific research questions. First, does graph description order affect LLM performance in solving graph problems? This is our fundamental question. Is there a measurable impact? Second, is LLM robustness to graph description order consistent across different tasks? In other words, are some tasks more sensitive to order than others? And third, are specific graph description orders better suited for certain graph tasks? Can we match orders to tasks for optimal performance? Let me walk you through how we systematically addressed each of these questions. To answer these questions, we designed a comprehensive framework. We take a graph and reorder its edge descriptions using different strategies: BFS, DFS, PageRank, and personalized PageRank. We tested on 6 graph tasks, ranging from simple connectivity detection to complex problems like finding Hamiltonian paths. All this data was organized into our GraphDO dataset, graph description with order. All of this resulted in our GraphDO dataset, graph description with order. This dataset contains 8,500 carefully filtered graph cases. Each graph has between 5 and 15 nodes, a range where LLMs have shown consistent reasoning abilities. Let me show you a concrete example. Here's the same graph described in two ways. In random order, edges appear as 6, 1, 6, 2, 0, 3, 4, 5. There is no apparent structure. But in BFS order starting from node 0, we get 0, 1, 0, 2, 0, 3, 0, 4, immediately revealing that node 0 is a hub connected to multiple nodes. This structural information emerges naturally from the ordering. This dataset is publicly available to support future research in this area. Our first major finding: order significantly affects performance. On traditional graph tasks, order descriptions improve accuracy by 12 to 70%. Even on node classification tasks, we see improvements from 1.9% to 14.82%. These benefits remain consistent across all prompting strategies. We believe this is due to attention bias in LLMs. The models give undue priority to certain parts of the input based on order. Our second finding relates to task complexity. Look at this variance chart. Simple tasks like connectivity and cycle detection show low variance. They're inherently robust to order changes. But complex tasks like Hamilton paths and shortest paths show much higher variance. They're highly sensitive to description order. Interestingly, even chain of thought prompting doesn't eliminate this sensitivity, suggesting a fundamental limitation in how LLMs process sequential information. Our third finding shows that different tasks benefit from different orders. BFS excels at local reasoning tasks. See these improvements of 14.1% for connectivity and 70.1% for shortest path. But DFS is superior for global exploration. It achieves 66.4% improvement over random order for Hamilton path, and even outperforms BFS by 22.3%. For node classification, probability-based orders like PageRank work best. You might wonder, is this just because order descriptions happen to match the answer? We tested this hypothesis. Even when we order edges to maximally overlap with the correct answer, accuracy only reaches 78.57%, still far from perfect. And when we minimize overlap, performance drops to random levels. This confirms that ordered descriptions genuinely improve structural comprehension, not just exploit answer patterns. Thank you for your attention.